We'll look at a few more practice problems in reference to percent composition in this video, and especially how we can use percent composition data in reference to the lab. Here's one more where we're going to calculate the mass percent of phosphate ions in calcium phosphate. So I do need the formula. Calcium is always +2. Phosphate -3. So I will need to fix this up a little bit to make it neutral. Calcium, I'm going to need 3. Phosphate, PO4, I'm going to need 2 groups to make this compound neutral at a +6 -6. 3 of these, 2 of those. So I do need parentheses around my phosphate group to show that I have 2 groups of phosphate. When I plug this in to get my molar mass, here's kind of what I'm thinking. In my calculator, I'm going to take calcium's mass, 40.08 times 3. Then I do need to distribute this 2 so that there will be 2 phosphorus and 8 oxygen. Phosphorus, 30.97. These are grams molar mass off my periodic table. There are 2 phosphorus. Oxygen, 16 grams per mole. And there are 8. So we're going to plug it all in. And wow, get a mass of about 310.18 grams. It's a big boy. All right. Now in the last video, we had one that just asked us for percent nitrogen in a big fat compound, but this one wants to know the mass percent of phosphate ions. So we're going to have something that looks like this. Percent phosphate equals. Now we mentioned earlier that the -3 charge means that you have 3 extra electrons. But in the end, who cares? Electrons have such a small mass that it's really insignificant compared to the mass of the overall atom. So the fact that there are 3 extra electrons will not affect the mass of my phosphate ion. I want this. This gives me the total amount of phosphorus and oxygen. Now you could add this up, 2 times the phosphorus, 8 times the oxygen, or you could go PO4 times 2, and either way, I should be looking at around, how about 189.94 grams of phosphate. So it's this. It's all the phosphorus and oxygen. And then just like any other percent composition, we divide by the mass of the compound. 18 grams of calcium phosphate. We'll multiply by 100 to make it a percent. And with about 2 decimal spots, 61.24% phosphate. -3. There, that's very manageable, right? We just add up everything that makes up the phosphate, all the phosphorus and oxygen. Now these last 2, these are the ones that I really like, because this starts bringing in some lab data. This is how we're going to use percent composition. In the lab, I could measure 10 grams of sodium chloride. Now let's say I wanted to do some kind of a chemical reaction where I decompose the sodium chloride. I separate the sodium from the chlorine. How many grams of sodium should be in that 10-gram sodium chloride sample? Ooh, so I could do this calculation and say, oh, I expect to get X amount of grams. Then I go in the lab, I really run the reaction, and I compare my lab data to what I expected from this calculation. We're going to start this with percent composition. what's the percent sodium in any sample of sodium chloride? Well, this one's an easy one. Percent sodium. Well, I know sodium chloride. I like this compound, +1, -1. It's a 1-to-1 ratio. Super easy. So I'm going to have 1 sodium, 22.99 grams of sodium, divided by the mass of the compound. Sodium plus chlorine. 58.44 grams of sodium chloride. Times 100 will give me, I'll keep it with the 2 decimal spots, I suppose, 39.34% sodium. Awesome. Now, in a former life, you might remember something called the law of definite composition. That says a particular compound must always be composed of the same elements in the same ratios in order to have the properties of that particular compound. So, for example, any sample of sodium chloride should be a 1-to-1 ratio of sodium to chlorine atoms. If it is always a 1-to-1 ratio of sodium to chlorine, then this percent will always be the same. Any sample of sodium chloride is 39% sodium by mass. True of any sample. Constant composition. The law of definite composition. So now watch, here's what we can do. I have 10 grams of sodium chloride. I have a 10-gram sample. 39.34% of any sodium chloride sample should be sodium. So what if I just multiply by my 10-gram sample? Now we'll have to multiply using that percent as a decimal. So 0.3934. Well, what do you know? Now this time I think I'll just leave 3 sig figs because my original lab measurement just had 3. 3.93 grams of sodium. If I really did this in the lab, I would expect about 3.93 grams of sodium. Then I compare that to the mass that I really collect. Hopefully they're the same. That is exactly what we'll end up doing in the lab. We'll calculate this theoretical percent. Any sample of sodium chloride should be 39% sodium by mass. Then we can use that along with our lab measurements. Well, I measured 10 grams of sodium chloride. It should be 39% sodium. We'll multiply using it as a decimal, and then we can get our expected lab results. We'll compare that to what we actually get. I love that. Love, love, love that type of calculation. So the last one is very similar then. Ooh, somebody measures 5.8 milligrams of iron 2 nitrate. That's a small sample. What mass is contributed by the nitrate ions? So very similar. Of that 5.8 milligram sample, how many milligrams are nitrate? So first we need to find the percent nitrate in the original compound, which means I do need to write the formula. It's iron 2 nitrate. So let's see here. I'm going to need 2 groups of nitrate. NO3, we'll put it in parentheses, we need 2. All right, so we can find the molar mass. You plug this in your calculator. I will need to distribute the 2 amongst both the nitrogen and the oxygen. So in my calculator, here's what I'm doing. Iron. On my periodic table, 55.85 grams. There's only one iron. Nitrogen is 14.01 grams. There are 2. Oxygen is 16 grams. There are 6 of them. I'm going to plug all this in and add them up. Remember, that 2 only goes to the polyatomic ion, not to the iron. Okay, so we're looking at 179.87 grams. Now, similar to a previous problem, I want to find the percent nitrogen in this compound. So I'll have something that looks like this. Percent nitrate. Nitrate ions. That's all of this. The 2 NO3 groups. It's okay that it's a -1 charge, so what? I have an extra electron. So these together, 124.02 grams of nitrate. 0.02 grams of nitrate divided by the compound, 0.87 grams of iron nitrate. Show me this work. Show me this mass. Show me this formula. I don't need to see the blue stuff. Show me the red. Times 100. So this would be about 68.95% nitrate. So almost 70% of the mass is coming from the nitrate ions, which then I can use my sample size, and it's okay that this is in milligrams. If we go 5.8 milligrams of the iron nitrate, we can multiply by 0.6895. We do have to use our percentage as a decimal. If it doesn't specify otherwise, I don't care if you leave this in milligrams. Your final answer will be in milligrams, which if I go like 3 sig figs, I would actually be looking at about 4 grams, 4.00 milligrams. Milligrams of nitrate ions. I'm okay if you leave it in milligrams or kilograms or whatever it might have been. Now, if the question said, what mass in grams is contributed by the nitrate ions, well, then I would have to flip the decimal spot and switch it from milligrams to grams. But if this one doesn't specify, I'm okay if you want to leave it. This is a great calculation. It really does serve a purpose for us in the lab. We could do a chemical reaction and we could prove this number. Any compound, any form of this iron 2 nitrate should be 68.95% nitrate by mass. We can apply that percentage to any sample size.